Hey guys, it's Richard, Ivan and Jeff here, and today we are going to talk about the intersections of planes and their possible systems.
But first, what is a plane? A plane is a flat two-dimensional surface that extends infinitely far. We can determine the vector equation of a plane by two non-parallel coplanar lines and a single point. We can identify planes with the symbol pi. There are two types of systems when it comes to planes. There is a consistent and inconsistent system. In a consistent system, there's one to infinite number of solutions, and in an inconsistent system, there's no solution.
When it comes to types of intersections, there is a case where all planes are parallel. We can identify this by comparing the direction vectors of the vector equation or normal vectors of the scalar equation to find if they have a similar ratio. In the case when all three planes are parallel, there's a scenario when all the planes are coincidents. Therefore, there's a solution that satisfies all three planes, making this system consistent. Moving on to our second scenario when all the three planes are parallel. The second scenario is when two planes are coincident and one distinct. There is no one solution that satisfies all three planes, thus making the system inconsistent. Moving to our last scenario when all three planes are parallel. Our last scenario is when all three planes are distinct. There is no one solution that satisfies all three planes, therefore this system is inconsistent. So when all three planes are parallel, they can be all coincidents, two planes can be coincident and one is distinct, or all the planes are just distinct.
Next, we will focus on our second case when two planes are parallel and one is non-parallel. In the case of when two planes are parallel and one is non-parallel, the first scenario where two planes are coincident and one is intersecting, they all intersect at a line. Therefore, there is a single solution that satisfies all three planes, making the system consistent. Moving on to our second scenario when two planes are parallel and one is non-parallel. The second scenario where two planes are distinct and one is intersecting. Therefore, there is no solution that satisfies all three planes, making the system inconsistent. There are two possible scenarios for this case: when the parallel planes are constant and non-parallel plane intersects, and when parallel planes are distinct and non-parallel plane intersects both.
Now we know that there are two possible cases for when two planes are parallel and one is not parallel. Next, we will focus on when all the planes are not parallel. First, we perform a volume test to determine if the three planes are coplanar or not. If they do not equal to 0, then they are non-coplanar and they intersect at a point. If the volume test equals to 0, the planes are coplanar. We then solve the system to determine if we get a contradictory or non-contradictory statement. In the case of a contradictory statement, the three planes intersect pairwise. Since there is no one solution that satisfies all three planes, the system is inconsistent. In the case of a non-contradictory statement, the three planes intersect at a line. Since there is a solution that satisfies all three planes, the system is consistent. Now we know that there are three possible cases for when all three planes are not parallel. They can intersect at a point, intersect pairwise, and intersect at a single line.
Now let's see how do we solve this system. As you can see, there are three scalar equations. First, we compare the normals. After comparing them, we find out they are not parallel. Then we perform the volume test. In volume test, we take the cross product of any two normals and dot product with the other normal. In the case, cross product can be written as n1 n2 equals to 1 times 3 minus 1 times 1, 1 times 2 minus 1 times 3, 1 times 1 minus 1 times 2. To get a new vector, 2, negative 1, negative 1. And now let's do the dot product. Using the cross product of n1 and n2 dot product with n3. Then we get a scalar quantity 7, which not equals 0. Thus, the plane intersects at a point due to the contradictory statement. After knowing the solution is a point, let's solve for the point of intersection. First, take equation 1 minus equation 2 to get equation 4. Then take equation 2 plus equation 3 to get equation 5. Using this, we take equation 4 minus 2 times of equation 5 to solve for x. Then sub the x value into equation 4 to solve for the z value. Then sub the x and z value into equation 1 to solve for the y value. And finally, the plane intersect at the point 214. The system is consistent.
Created using Powtoon.